Welcome to week 6, everyone. Hope you had a nice weekend and got outside to enjoy the nice weather. I know it's supposed to be a little bit cooler and maybe not as sunny this week, but probably maybe helpful for getting back to some schoolwork. So you guys, this week is going to be the review for the quiz, and then next week we're going to have a, I think, fairly short quiz on what we've been doing since spring break. And this first screen, I'm going to kind of talk through kind of quickly, is just the names of the topics of things that we've been working on. So spanning trees, minimum spanning trees, Kruskal's algorithm, weight of a graph, Hamilton circuits, traveling salesperson problem, best edge algorithm, brute force algorithm, and then Euler circuits is a previous topic that I just wanted to kind of compare Hamilton circuits to. So this video is going to kind of go through and hit on some review of what these topics are. All right, so the first one is, what is a spanning tree? And it's a graph that's based on, an existing graph, and that new graph has to connect all the vertices of the original graph. And then this graph to the left, ABCD, has 4 spanning trees that start at vertex A. You could actually make more that start at different vertices, but the ones that I drew for this example are just all starting at A. So down here is one. I highlighted what one of the spanning trees would look like if you started at A and went to C and B and D. So basically we've connected all the vertices of the graph. And then if we take those highlighted edges and just show them what they would look like, over here on the right is what the spanning tree would look like for this graph at the top. And then I just wrote out what the letters, if I started at A, the order that I might go in is A, C, B, D. And if I add up those edges, I get a weight of 105. Right. And then this page is just showing other spanning trees that would also, oops. Okay, I accidentally closed that, so hopefully it's back to working here. So what I was just saying is that this page is showing other spanning trees for that same graph. I could start at A and go to B and then D and then C, and that would look like this graph down here. It has a weight of 95 when I add them up. I could also go A, C, D, B, and that would have a weight of 100. I could also go A, B, C, D. And those are just ones that, if I wanted to start at A, again, I could pick a different vertex to start at, but so there's more than 4 spanning trees. I just was giving some examples of them. All right, and then if we were trying to find the minimum spanning tree, it's of all the spanning trees that you could make, it's the one that uses the minimum length of edges. So we did have a process. Instead of just trying to figure out all the spanning trees and find the minimum one, you can actually follow these steps, which is referred to as Kruskal's algorithm. It's a process for finding a minimum spanning tree. And we had this in a previous day notes, which I'm going to link the old videos to this week's Google Doc also. So step 1 is just to draw the vertices. Step 2 is to add the edge with the smallest weight. You're not supposed to create a circuit, so I just started with the smallest one, which is 20. Then if you go on to step 3, you're supposed to keep repeating step 2 as long as you don't make a circuit. So the next minimum would have been the 25, and then the next minimum after that would have been the 30, and then you can see that you've connected all the vertices. So this is a spanning tree, and it's actually the minimum one because we followed the Kruskal's algorithm. So all the vertices are connected, and if we add up those weights here on the next page, 30 plus 25 plus 20 would add up to 75. So we say that the weight is when you add up the edges of that graph, and this minimum spanning tree has a weight of 75. And because it is the minimum spanning tree, it should be the minimum weight possible for any spanning tree for that original graph. Okay, this one's just to remind you what an Euler circuit was. This was one of the very first things we did in the semester. An Euler circuit is when, kind of like the painting the lockers problem, or mail delivery or garbage pickup, when you have to get to every road. It's a graph that you can start and end at the same vertex and trace each edge exactly once. And we know this is possible when all the vertices have even degree. So I know there's a lot of edges in this graph, but if you count, each one does have 4 edges coming into each vertex. So they are all degree 4. So then we would know it's an Euler circuit. And then I just picked a letter to start at and show how you could go from E, D, C, A, B, E, and then to C, to B, to D, to A, and back to E. So in that highlighted version, I covered all of the edges of the graph and got back to E. So that's the purpose of an Euler circuit. All right, what we did new this semester was something called a Hamilton circuit. And for a Hamilton circuit, you're not trying to get to all the edges. What you're trying to do is start and end at the same place, same vertex, and visit all the other vertices exactly once. So I used capital letters. I know these are lowercase, but you could start at E, go to F, to D, to A, to B, to C, and come back to E. So I hit all of the vertices of the graph, and I came back to where I started. Here's just some other Hamilton circuits that you could have done for that same graph. This one on the left, I started at C and kind of went around this way. This one I started at D. Again, it doesn't really matter what letter you start at. And I went around this way. So there's several options for the Hamilton circuit for this graph. Okay, now what we're trying to do with the Hamilton circuits is try to find a Hamilton circuit that has the minimum weight. And this was referred to as the traveling salesperson problem, because the idea is like you want to hit every city, for example, and if the distances were miles, right, you want to hit every city, but also travel the least amount of distance. So that's why we're looking for a Hamilton circuit that has a minimum total weight. And there's a couple strategies that you can use to do this. There's the best edge algorithm, which I'm going to list again step by step, which was in another video that we had, I think on week 4 maybe. And then there's the brute force algorithm. And remember these strategies, the best edge one doesn't always find the best solution, and the brute force one can be pretty inefficient, although it should find the best answer. Okay, so here's the step-by-step. I just actually copied and pasted from the previous video that we had done. And it's a little more complicated than doing a minimum spanning tree, but you make a copy of the graph, and it says with the edges drawn lightly. You can do that, or you can just work on like highlighting them instead of dark. This one says darken the shortest edge not used. So what I did, kind of just did this all in one graph here. I started with 1 because that was the minimum shortest edge, and then you keep adding in the next minimum. But the things you don't want to do is you don't want to create a circuit, unless all the vertices are included, and you don't want any vertex to be touched by 3 darkened or highlighted edges. Okay, so 1, drawing this edge is fine. Drawing this edge, that's 2, is fine. I haven't made a circuit. I haven't touched 3 edges to 1 vertex yet. 3 is okay. 4 is okay also. Okay, then I have 3 different edges that are 5s, and I cannot put in this 5. Well, actually, okay, I put in this 5 first, and I also put in that 5. I can't put in this 5, and I don't need to, is because it would create a circuit right there. And I've already like connected all of my vertices together already. So by following this process, I did find a Hamilton circuit that should have the minimum weight to it. Okay, I guess one thing I didn't do is I never actually added up the weight to this. So I'll just do that quick. So 1 plus 2 is 3, plus 5 is 8, plus 4 is 12, plus 5 is 17, and then plus 3 more would be 20. So the weight of this traveling salesperson problem, let's say these were miles, would be like 20 miles to travel to all the cities in the least amount of distance. Oops, so that was my error. I guess I forgot to do the total weight there. This one's just a reminder more about what the brute force algorithm is. Again, it's not an efficient process, but it should always find you the solution. The process is to find all the Hamilton circuits possible, which could be a lot, and then calculate the weight of each one, and then whichever one weight you find is the minimum, that would be the solution to the traveling salesperson problem. Okay, so I've kind of hit on all the main vocabulary and algorithms that we've been doing since break. And now I just have a couple practice problems that I want you guys to try. I included them in this video, but they're on Schoology. And actually I didn't put the pictures in Schoology, I just put the questions there. So you will need to pause the video and look at the pictures I have included here. So the first one is just using the Kruskal's algorithm to find a minimum spanning tree and the minimum weight. So you'll find 3 questions in Schoology for that one. And then the second question is to use the best edge algorithm to solve the traveling salesperson problem. Here's your graph. There's 2 questions related to that graph. All right, so that's our review. Yep, the quiz will be coming next week. So please let me know. I'm going to obviously look at your Schoology answers and give you some feedback on those. But if you have questions as you're working through those, this would be maybe a good week to check in with me, either via an email message or I do have office hours at 2 o'clock every weekday. And there's the link is in my Google Doc Schoology letter to you guys every week. Or if that time doesn't work, we can always set up a different time and I can help you out. So good luck with these and keep in touch. Thank you.